In this video, we want to explore the probability of the union of sets. Now, we saw in the last video that if A and B were disjoint, so their intersection is empty, then the probability of A union B is equal to the sum of the probabilities. That was axiom 3. And we can see that if I draw a Venn diagram. It's a nice way to illustrate it. So we have A over here, and we're assuming that it never intersects with B. That's over there. So this is right here, the probability of A plus the probability of B, and that gives me the union of those two sets. But what happens if A and B are not disjoint, or I don't know if they're disjoint? And so I want to account for the case where they may have an intersection. So I draw my Venn diagram this way. And notice now, if I add all of A, and then I add all of B, I'm actually adding this intersection 2 times. And so I can subtract off one intersection of A and B, and that'll give me the union. Okay, and we can actually see this mathematically, not just with the Venn diagram. So remember a couple of things. Let's take this Venn diagram right here and write it as the union of disjoint sets. So I have A union B, and I see that the blue is A, so A, and then just the green now is the stuff that's in B but not A. So it is in union not A and B. All right, so I've now written the probability of I've written A union B as the union of disjoint sets, which means by axiom 3, the probability of A union B equals the probability of A plus the probability of not A and B. All right, now we're going to do another drawing. We're going to write B as the union of disjoint sets relative to A. So B can be expressed as A and B union not A and B. So I've written B as the union of disjoint sets, which means the probability of B is equal to the probability of A intersect B plus the probability of not A intersect B. Now, I'm going to solve for this down below. So if I have this by itself, I get the probability of B minus the probability of A and B is equal to the probability of not A and B. So I'm going to replace this right there with this. So coming down here, I have the probability of A union B equals the probability of A plus, now insert this, the probability of B minus the probability of A intersect B, which we showed above with the Venn diagram, but mathematically we could show it with our axioms. Nice. So what about if we have 3 sets? So let's draw a Venn diagram with 3 sets. So A, B, and C, and all the possible intersections. And what we are curious about is the probability of A union B union C. Well, we could systematically write all of these as the union of disjoint pieces and sum them up, but it might be quite tedious. And in practice, that is also tedious. What would be nice is if we could not worry about it, add up all of A, all of B, and all of C, and then deal with the overcount. And notice that if we add up, let's do it with a highlighter here. If we add up all of A, and then if we add up all of B, so notice I'm counting that football twice. And then let's add up all of C. So I've counted each football twice, but the one in the very, very center, this one right here, I've added 3 times. So if I subtract off the intersection of A and B, then that removes, let's see if I can remove it. It removes that 1 time, but it also removes our middle football 1 time. If we then subtract off B and C, then it's going to remove that 1 time, put it back in, and the middle football 1 time. So it's now been removed twice. And then if I then subtract off A intersects C, then it's going to remove this one 1 time. And at this point, we've now removed that middle football 3 times. And so we're down to 1 on each of those little pieces, but the way we fix it is we're going to add back in the intersection of all 3. And in fact, this is what is the case for the union of, we'll say A1 union A2 union all the way up to, we'll say A sub n. If we want to find the probability of the union of n sets, and I know not whether they intersect or not, we're going to start by adding up all of the probabilities. So we'll write it in summation. So the probability of A sub I equals 1 up to n. So that's like A1, A2, A3. Now we're going to subtract off all of the intersections. So we'll say the probability of AI intersect AJ. And so we don't double count that. We'll say I less than J. And then we're going to add back all of the triples, however many those are. So we're going to write it like I less than J less than K, because we don't want to count for all the permutations of the AIs. AI intersect AJ intersect AK. And we're going to keep doing this process, subtract, ... And we're going to keep doing it until we get to the very last one. And we're either going to, let me write it on the next line. Come down here. Plus, it's either going to be a negative or a positive depending on, and this is going to be the intersection of them all. Intersect IJ, intersect A, sorry, this should say A1, A2. Because this time we're getting them all. It's eraser. So A1, A2, intersect AN. And if it's even, if n is even, then you're going to be subtracting off that last one. So if n is odd, we want it to be negative. So we're going to do n plus 1. And that is the inclusion-exclusion principle.